Let's work an example impulse momentum problem. It says a golf ball of mass 0.045 kilograms is hit off the tee at a speed of 45 meters per second. The golf club was in contact with the ball for 0.0035 seconds, and we're supposed to find the impulse and the average force exerted on the ball by the golf club. I like to start things with a picture, so here's my golf ball sitting on a golf tee. This is my initial picture because nothing has happened yet. So I have an initial velocity of 0 meters per second because my ball's at rest. Now a little bit while later, here's my picture. Okay, and now the ball is moving this way. It has a velocity, and its velocity is 45 meters per second. So it's just coming off the tee. Of course, it's coming off the tee because a golf club, bam, hit it. Alright, so I know initial velocity, I know final velocity, and I know one more thing. I know that it took 0.0035 seconds. The collision lasted that long. We're supposed to find the impulse and the average force exerted on the ball. Well, impulse is equal to force times time. I don't have a force, but it is also true that force times time is equal to change in momentum. So if I can find the change in momentum, I can find the impulse. So I do know a change in velocity, and I do know a mass. So the mass of this thing is 0.045 kilograms. So I'm just going to go ahead and I'm going to say, all right, well, delta P, change in momentum, is equal to, in this case, change in velocity times mass. I say in this case because the mass remained constant. Sometimes you can do problems with rockets and the mass changes. So change in velocity, final minus initial, 45 minus 0 times its mass, 0.045. So 45 times 0.045 is 2.025 kilogram meters per second. Okay, that's the change in momentum, so it is also the impulse that the ball felt. Okay, 2.025 kilogram meters per second. Now B says let's find the average force. Well, because force times time is impulse, I can just say, okay, well, this will be an average force because it's acting over the whole duration. In reality, this force time graph looks like this, right? But we are using the average force to find it. So we're not going to get the maximum spike. We're just going to get the average. So F times 0.0035 is equal to 2.025, and I can divide both sides of this by 0.0035, and I get a force of 578.6 newtons. That seems like a really, really big force to try to make a golf ball move, but it is that large because the duration of the impulse was actually very small. So I sketched a force time graph over there, but really my force time graph should look more like a spike and less like a curve, because nothing acts on the ball, nothing acts on the ball, nothing acts on the ball, and then all of a sudden, bam, it gets hit. And it gets hit really, really hard, and then it flies away. And so this force actually didn't act for a very long time. Okay, you could do the same thing and make the ball get going just as fast by slowly increasing and then pushing on it over a very, very, very long time and doing that. Okay, but we didn't. Okay, so the force that acted on the ball was 578.6 newtons. It only acted for 0.0035 seconds. That caused an impulse of 2.025 kilogram meters per second, which made the ball speed up from rest to 45 meters per second. Okay? So impulse momentum allows us to look at a before and after picture without looking at exactly everything that happened in between.